The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so this is the start. I won't be able to do it all in one day of what I think of as the number one model in applied math, in discrete applied math, I'll say. Let me review what our four examples are, just so you see the big picture. So the first example was the springs and masses. That was beautiful. It's simple. The masses are all in a line, and the matrix K, the free fixed and fixed and free come out closely related to our K, T, B matrices. So that was the natural place to start. And actually, we also got a chance to do the most important time equation in time. Ku double prime, mu double prime plus Ku equals 0. So that's a key example. Then these squares, very important. I'm already getting questions from the class about problems that come up in your work, least square problems. Maybe I'll just mention that the professional numerical guys don't always go to A transpose A. If it's a badly conditioned problem, and that conditioning is a topic that was in 1.7 and we'll eventually come back to, if it's a badly conditioned problem, matrix A, then A transpose A kind of makes it worse. So there's another way to orthogonalize in advance, and if you're working with orthogonal vectors or orthonormal vectors, numerical calculations are as safe as they can be. You know, Wall Street is more like A transpose A, and the orthonormal is the safe way. Okay. All right. This is today's lecture. You'll see the matrix A for a graph or a network. It's simple to construct, and it just shows up everywhere because networks are everywhere. And I'll just, looking ahead, trusses are there partly because they're the most fun. You'll enjoy trusses. I mean, it's kind of fun to figure out, is the truss going to collapse or not? It's good. And what's the linear algebra in there? The collapsing or not will depend on the solutions to AU equals 0. Let me just recall the equation AU equals 0. A is our key matrix in each example. It's different in each example. And we sort of hope that AU equals 0 doesn't have solutions, or that it has solutions we know. Because if AU equals 0 has solutions, that's the case where A transpose A is not invertible and we have to do something. Okay. Very useful to review. What were the solutions to AU equals 0 in the case of springs? Well, there were some in the free case. The all ones vector was the solution U, or all constant was the solution U in the free case, and that's why we couldn't invert it. But the fixed free or the fixed, when we have one support or two supports, that removed the all ones solution. Good. These squares, we assumed there weren't any. We assumed, because we wanted to work directly with A transpose A, the normal equations, and so we assumed that the columns of A were independent. We assumed that there were no non-zero solutions to AU equals 0, because if there were, that would have made A transpose A singular, and we would have had to do something different. Here, this will be a lot like this one. Today, if we look at, once you see A, you'll spot the solutions to AU equals 0. This is A for a network, and the solution is going to be that same guy, all ones. And that only tells us again that we have to ground a node, if I may use an electrical term here. Grounding a node is like fixing a displacement. Once you've fixed one of those, say it's 0, whatever, but 0 is the natural choice. Once you've said one of the potentials, one of the voltages is 0, then you know all the rest. You can find all the rest from our equation. So this is like this in having this all one solution. And as you'll see with trusses, that could, depending on the truss, have more solutions. And if there are more solutions, that's when the truss collapses. Yeah. So the trusses need more than just a single support to hold up a whole truss. Okay. Okay, so that's the AU equals 0. Now we're ready for the lecture itself. Graphs and networks. Graphs and networks. Okay, let me start with it. What's a graph? A graph is a bunch of nodes and some or all of the edges between them. Let me take just a particular example of a graph, and this, of course, you spot in the book. Oh, and everybody recognized that, and it's probably now corrected, that in that homework where it said 3.4, it meant 2.4, of course. And this is section 2.4 now. Let me draw a different graph. Maybe it'll have 4 nodes, has those 4 edges. Let me put in a 5th edge. Okay, that's a graph. It's not a complete graph because I didn't include that extra edge. It's not a tree because there are some loops here. So complete graphs are are one extreme where all the edges are in. A tree is the other extreme where you have a minimum number of edges. It would only take probably 3 edges. So just while we're looking at it, there are a bunch of possible trees that would be sort of inside this graph, subgraphs of this graph. If I knock out those 2 edges, I have a tree going out, or a tree could be like this, or a tree could be like this. Anyway, 5 edges is in this graph, 6 in a complete graph. It would be 3 edges in a tree, I guess. Okay, and the number of edges is always m. So 5 edges. And the number of nodes is always n, 4 nodes. So A will be 5 by 4. Okay. And it's called, so we get a special name in this world, it's called the incidence matrix of the graph. The incidence matrix. Or, of course, these things come up so often they have other names too. But incidence matrix is a pretty general name. Okay. It doesn't, yeah. Okay, now I have to number the nodes just so we can create the matrix, say 1, 2, 3, 4. And I have to number the edges. If I don't number them, I don't know which is which. So let me call this edge 1 from 1 to 2, and I'll draw an arrow on the edges. So from 1 to 2, maybe this will be edge 2. From 1 to 3, this will be edge 3. Oh, no, let me put edge 3 there. Would be a natural one, say from 2 to 3. And how about edge 4 there, from 2 to 4, and edge 5 going from 3 to 4. Okay, so now I have numbered, I've identified the nodes and I've identified the edges. And there were 5 edges and 4 nodes. Usually, m is bigger than n. We're in this, except for trees, m will be at least as large as n. Okay, so now, and I've put arrows on, so you could say it's a directed graph because I've given a direction. You'll see that the directions, those arrow directions, which are just to tell me which way current should count as plus if it's with the arrow, or which way it should count as minus if it's against the arrow. Of course, current could go either way. It's just now I have a convention of plus, which was plus and which is minus. Okay, so now let me tell you the incidence matrix. So everybody can get it right away. How do you create this incidence matrix? A, 5 by 4. So it's going to have 5 rows, 1 for every edge. So what's the row for edge 1? And it's got 4 columns, 1 for every node. So these are the nodes. Nodes 1, 2, 3, 4 are associated with. So there's a column for every node and a row for every edge. Okay, edge 1. This is just going to tell me everything about the graph. So exactly what's in that picture will be in this matrix. If I erased one, I could reproduce it by knowing the other one. Okay, edge 1 goes from node 1 to node 2. So it leaves node 1. I'll put a minus 1 there in the first column and a plus 1 in the second column. So that's telling, and it doesn't touch, edge 1 doesn't touch nodes 3 and 4. So there you go. That's edge 1. Let me do edge 2, and then you'll be able to fill in the rest. So edge 2 goes from 1 to 3, minus 1 and a 1. Edge 3 goes from 2 to 3. I'll just keep going. Whoops. Minus 1 and a 1. Edge 4 goes from 2 to 4. And edge 5 goes from 3 to 4. Okay. Simple, right? Got it. That matrix has got all the information that's in my picture. And the matrix, but the point about matrices is they do something. They multiply vector u to produce something. You know, they have a meaning beyond just a record of the picture. So that's, A is a great thing. In fact, what does it do? Let's see. Okay, so that's the matrix A that we work with. Oh, first tell me about AU equals 0, because we brought up that subject already. What are those 4 columns independent? I've got 4 columns. They're sitting in 5-dimensional space. There's plenty of room there for 4 independent vectors. Are these 4 columns independent vectors? No. No, they're not. Because what combination of them produces the 0 vector? 1, 1, 1, 1. If I take that column plus that, plus that, plus that, I'm multiplying by, so A, I'll just put that up here, and then I won't have to write it again. A times 1, 1, 1, 1 is 5 zeros, right? So that U, that particular U of all ones is, it's, I would say, in the null space of the matrix. The null space is all the solutions to AU equals 0. And in other words, so these 4 columns, tell me about the geometry again. These 4 columns, if I take all their combinations, yeah, think about this. If I take all 4 combinations, all combinations, any amount of this column, this column, this column, and that 4th column, those are all vectors in 5-dimensional space. Now, this isn't essential, but it's good. Do you have an idea of what you'd get? What would you get if you took, so this, think of 4 vectors pointing along, take all their combinations, that kind of fills in, whatever fill in may mean. And what does it fill in? What do I get? Well, what do you think? What's your image of it? It's, frankly, I don't know. I can't visualize 5-dimensional space that well, but still we can use words. What do you think? You get a something subspace. You get a something, you get something flat. Can I don't know if you do. It's pretty flat somehow. Like I'm just asking you to jump up from a case we know where we had columns in 3-dimensional space, and we took a combination and they gave us a plane, right, when they were dependent. Now, how would you visualize the combinations in 5-dimensional space, just for the heck of it? it's some kind of a subspace, I would say. And what's its dimension? Maybe that's what I want to ask you. What's the dimension? Do I get like a 4-dimensional subspace of 5-dimensional space when I take the combinations of these particular 4 guys? Yes or no? Do I get a 4-dimensional subspace, whatever that may mean? No. Right answer, I don't. I don't. Somehow the dimension of that subspace, whatever I get, isn't 4 because this 4th guy is not contributing anything new. The 4th one is a combination of the first 3. So I get a 3-dimensional subspace. The rank of this matrix is 3. That's if you allow me to introduce that key word, rank, is sort of, it's the number of independent columns. It tells you how much, how big the matrix really is. You know, if the matrix, if I pile on a lot of 0 columns or a lot of 0 rows, you know, the matrix looks bigger. But of course it isn't truly bigger. The heart of the matrix, the core of the matrix, is somehow just 3. And actually, I tell you now, and we'll see it happen, can I tell you the key result in the first half of linear algebra? It's this, that if I have 3 independent columns, and by the way, any 3 are independent, it's just all 4 together are dependent. This has 3 independent columns, then the great fact is it has 3 independent rows. That's kind of fantastic. Can I just, since it's like such a beautiful and remarkable and basic fact, that look at the rows. That's what linear algebra is all about. Looking at a matrix by columns and then by rows and seeing what are the connections. And the connection is, the key connection is, that these 5 rows, now what space are they in? What space are these rows in? 4-dimensional space. They only have 4 components. So I had 4 columns in 5D. I have 5 rows in 4D. But now, are those 5 rows independent? Let me just ask that question. Are those 5 independent rows, are they pointing in different directions? Or could any combination give the 0 vector in 4D? So looking at those 5 rows. What do you say? Wait a minute. 5 vectors in 4-dimensional space? Dependent, of course. Right. So they're certainly dependent. They couldn't be 5 independent vectors in 4D. But are there 4 in this particular case? And here's the great fact. No, there are 3. If there are 3 independent columns and no more, then there are 3 independent rows and no more. And we'll get to see which rows are independent and which are not. That's a question about A transpose, and we haven't got to A transpose yet. Okay, are you okay with that incidence matrix? Because this is like the central matrix of our subject. And why don't we can figure out A transpose A. That's kind of fun. If I do A transpose A, then you'll see the core computations of this neat section. So if I do A transpose A, so I'm going to bring in A transpose, and you know that I'm not just bringing it in from nowhere, that networks, the balance law is going to involve A transpose. So, but let's just anticipate. What do you think A transpose A looks like? Now, how am I going to do this for you? May I erase this for a moment and try to squeeze in A transpose here so that you can multiply it by sight and see the answer, and then you'll see the pattern. That's the great thing about math is you do a few examples and you hope that the pattern reveals itself. So let me show A transpose. So now I'm going to take that column and make it a row. I'm going to take that column and make it a row. It's going to be a little squeezed, but we can do it. Take that column, 0, 1, 1, 0, minus 1, and the last column 0, 0, 0, 1, 1. Okay, so I just wrote A transpose here. And now could you help me with A transpose A, which is the key matrix in graph theory? What size will it be? Everybody knows it's going to be square, it's going to be symmetric, and just tell me the size. 4 by 4, right? We have a 4 by 5 times a 5 by 4. We're expecting this to be 4 by 4. And what's the first entry? 2, right? Take row 1, dotted with column 1. I get 2 1s and then a bunch of zeros, so I just get a 2. What's the next entry? Take row 1 against column 2. Can you do that in your head? Row 1, column 2. The top one is going to hit on a -1, and I think that's all there is, right? Then this one hits a 0 and those 3 zeros. So, and then what about the next guy here? A -1, and the last guy? A 0. So that's row 1 of A transpose A. Can I just look at that for a moment before I fill in the rest? And then when you fill in the rest, it will confirm the idea. Why do I have a 0 there? I shouldn't say I have a 0. Why did a 0 appear in the 1, 4 position? Well, if I look back at the graph, what is it about nodes 1 and 4 that told me ahead of time? You're going to get a 0 in that A transpose A. Everybody sees it? Nodes 1 and 4 are? Yeah, say it again. Not connected. No edge. Here there was an edge from node 1 to 2. There's an edge from node 1 to 3. Those both produced the -1s, and on the diagonal came the 2 to balance it. What does that 2 represent? That 2 represents the number of edges that do go into node 1. See, that row is all about node 1. So there are 2 edges into it, and then an edge out, and an edge, the edge out, and the edge out, and the no edge. Okay. So now I know it's going to be a symmetric matrix, so I could speed up and fill those in. What's the next entry here? What's the guy on this diagonal? So that's row 2 against column 2. So I have a 1 there, a 1 there, a 1 there. That makes a 3. Why a 3? Because there are, yep, you got it. There are 3 edges into node number 2. 3 edges into node number 2. And now I'm going to have some -1s off the diagonal for those edges. And what are these entries going to be here? They're both -1s. Edge 2 is connected to all 3 other nodes. So I'm going to see a -1 and a -1 there, and it's going to be symmetric. And I'm nearly there. What about, of course, I'm describing a pattern that you're just seeing unfold, but I'm doing it that way so that you'll feel, hey, I can write down A transpose A or check it quite quickly without doing this complete matrix multiplication. So what number goes there? That's to do with node 3, and I see node 3 connected to all 3 other nodes. And so what do you expect there? -1 there and a -1 there. And what do you expect here? 2. And so now I have my matrix, the A transpose A matrix, and it's square and it's symmetric. Now I ask you, is it positive definite or is it only semi-definite, right? We know that A transpose A is always positive definite in the best case, but only positive semi-definite if it's singular, if there's some vector in its null space, if A transpose A times some vector gives 0, if some combination of those columns gives me the 0 column. Which is it? Have I got a singular matrix or an invertible matrix here? Singular. Singular. Why singular? because A had some solutions to AU equals 0. So if AU equaled 0, then I could multiply both sides by A transpose. That same U, A transpose times 0, will still be 0. It might be a different size 0, but it'll be 0. And what's the U then? It's the all ones vector. What am I saying about the columns of A transpose A? They're dependent. They add up because it's the 1, 1, 1, 1 vector that's guilty. Every row adds to 0. Every row adds to 0. Right. Let me just say for a moment, introduce a notation for the diagonal matrix, D. That's the diagonal matrix, 2, 3, 3, 2. And then I'll put in a minus sign, and this is called, and I'll call it W. So you can pick out what D and W are, but let me do it for sure. So D, the degree matrix. See, this is like fun because I'm not doing anything yet. I'm just giving names here. 2, 3, 3, 2. The degree of a node, the degree means how many edges go from it, how many edges touch it. And W is called the, what's it called? It's also a great matrix. It's called the adjacency matrix. Adjacency matrix. It's also beautiful. It's the, now it'll have plus ones because I wanted minus W. So it has, these nodes are not adjacent to themselves, but it's got this 1 and this 1 and this 1 and this 1 and that 1, and that's a 0. So there are 5. The adjacency matrix tells me which nodes are connected to which other nodes. And of course, the connections are going both ways. So I see 5 ones from 5 edges, and I see 5 more ones below the diagonal because the edges are connecting both ways. 1's connected to 3, and 3 is connected to 1. 1 is not connected to 4, and 4 is not connected to 1. 1 is not connected to itself by an edge. If we allowed like little self loops, then a 1 could appear on the diagonal, but we don't. Okay, so that's D and W. Here are the key matrices. This is actually, I venture to say that any afternoon at MIT, there's a seminar that involves these matrices. One name for this is the graph Laplacian from Laplace's equation, and we'll see pretty soon where that name is coming from. But it's there. And should I think I should just, about networks. Like, where did the network come from? I just think we got networks all around us, right? Electrical networks are the simplest, maybe in some ways the simplest to visualize. So that's the example. That's the language I'll use. I'll use the language, well, yeah. So I might put, I'm thinking of everything's going to stay linear. So if I wanted this to, so a graph I've got. Now I get a network. I use the word network when there's a C1, C2, C3, C4, C5. You know, those extra numbers. I've got the A, and now the network comes from the C part, that diagonal matrix. And if I'm talking electricity, these could be resistors. Instead of springs, they're resistors. So it's the conductance in those 5 resistors that are C1, C2, C3, C4, and C5 that so I'm ready for that. Ready for the C matrix because we got the A matrix. And we've got A transpose A, but you know that the applications throw in the C matrix also. What are other applications? I was saying, like, this one is the one I'll use the word currents for flow in the edges, or I'll use the word flow. A network of oil or natural gas or water pipes would be just that. The electrical, people study Professor Verghese in course 6 studies the electric grid, the U.S. electric grid, or often the western half of the U.S. electric grid. So that's got a whole lot of things. Pumping stations, you see it. Actually, the World Wide Web, the internet, is a giant network that people would love to understand. And the phone company would love to understand the network of phone calls. I mean, those are really, that's what giant businesses are dependent on, understanding and maintaining networks. Okay, so I'm going to use resistors. Of course, I'm staying linear, and I'm staying steady state. So by staying linear, there aren't any transistors in this network. By staying steady state, there aren't any capacitors or inductors. Those guys would be linear elements, but they would be coming in a time-dependent problem, a UTT problem. And I'm just staying now with the K, U equal F. I'm trying to create K, the stiffness matrix, which maybe here we might call the conductance matrix or something. Okay, so ready for the picture now that these come into? You know what the picture looks like. It's going to have the usual we'll start with these potentials U at the nodes, potentials at nodes. So those will be U1, U2, U3, U4. Voltages, if I'm really speaking, the units would be volts and now comes the matrix A. And now I get, what do I get from A? What do I get from A? Key question. If I multiply A times U, and you know that's coming, right? If I multiply A times U, so I'll erase A transpose now, because we've got that. So there's A, but now I'll make space to multiply by U. All right? So now I want to look at A, U. So A multiplies a bunch of potentials, a bunch of voltages, and let's just do this multiplication and see what it produces. This is the great thing about matrices. They produce something. Okay, what's the first component of AU? Of course, AU is going to be 5 by 5. It's going to be associated with edges. Right? U is associated with nodes, AU with edges. Just the pattern is so nice. All right, what's the first component? Just do that multiplication, and what do you get? U2 minus U1. What do you get in the second component? Do that multiplication, and you get U3 minus U1. The third one will be U3 minus U2. The fourth one will be U4 minus U2, and the fifth one will be U4 minus U3. Just like our first difference matrices, which were, but this one deals with, they're exactly, our first difference matrices were exactly like this when the graph was all in a line. The big step now is that the graph is not in a line, not even necessarily in a plane. Could be in it's a bunch of points and edges. Actually, the position of those points, we don't have to know, are they in a plane? I think of them as nodes and edges. Okay, so what's the natural name for AU? I would call those potential differences, right? Voltage differences. So that's what we see here, and those will be E. E1, E2, E3, E4, E5. will be potential or voltage differences. Voltage drops, you might. Potential differences, voltage drops. Oh, well, now, when I say voltage drops, that's because, as we noted before, the current goes from a higher to a lower potential. It goes in the direction of the drop. And I think that what we need now is minus AU for E. So E, I think we need a minus sign, and it's quite common to have the minus sign. We saw it already with least squares. Okay. And let me say also, so this is E. I'll abbreviate those 5 E's. I just wrote down 5 of them so you would remember there are 5. We're talking about currents. We're talking about, this is the E in E equal IR, the electromotive, the voltage drop that makes some current go. Now, also, just as with least squares, so it was great that we saw it before, there could be a source term here. So this, I'm completing the picture here, allowing the source term. And we'll come back to what does that mean physically. But at that point could enter B, and B is really standing for batteries. I work hard to make the language match the initials of these letters. Okay, now what? Okay, that step just involved nothing physical. Now comes the step that involves C, so W will be CE, and these will be the currents on the edges, and that's the law. Then, with a matrix C, of course, C is our old friend C1 to C5, and well, tell me first the name. Whose law is this? That the current is proportional to the voltage drop? Ohm's law. So this is Ohm's law. Instead of Hooke's law, it's Ohm's law. Right. And I've written it with conductances, not resistances. So resistances are 1 over R's. The usual R in E equal IR would be, I'm more looking at it as I current equals CE instead of E equal IR. So I'm flipping the resistance or the impedance to give the conductance. Okay, and now finally, can you tell me what the last step is going to be? If life is good. Well, you might wonder whether life is good reading the papers, but it's still good here. Okay, what matrix shows up there? Everybody knows it. A transpose. So the final equation, the balance equation, will be, let me write it so I don't catch it up here, will be A transpose W equals whatever, will be the balance equation. The current balance, it's a balance of currents, balance of charge, whatever you like to say. At each node, it's the balance at the nodes, because when we're up on this line, we're in the node picture. We have 4 equations here, right? We're talking about at each node. Here we're talking about on each edge. It's so critical. These 2 variables, which we're seeing physically as node variables and edge variables. The pair of variables just shows up everywhere in displacements and stresses is fundamental in elasticity. And there are just so many in optimization. It's everywhere, and a big part of this course is to see it everywhere. Okay, so why don't I just, so you see the main picture. We're going to have the A transpose CA matrix that I'm going to maybe call K again. And now, of course, there could be current sources, just the way there could be forces that we had to balance. There could be, not always, but there could be current sources from outside, external current sources. So these are external voltage sources. These are external current sources. So in a way, we now have combined our first two examples. Our springs and masses only had forces external. Our least squares problem had an external B, measurements. This picture is the whole deal. It's got B and F. And actually, I could put in even a little more sources like, well, we already kind of caught on to the fact that if we better ground a node or A transpose CA as it stands, A transpose CA as it stands will be singular. You know, it's the matrix, there's A transpose A, and the C in the middle isn't going to help any. That's singular. If we wanted to compute, be able to compute voltages, we've got to set one of them. You know, it's like setting one temperature. It's like deciding what, you know, where is absolute zero. Let's put absolute zero down here. U4 equals 0. Grounded the node. Okay. So that is we fixed a potential. So we fixed, here's a boundary condition coming in, U4 equals 0. That's another source term, another thing coming, you could say, sort of from outside the A transpose CA. We could fix another voltage at, I mean, I'm thinking now about, you know, what's the picture? What's the whole problem? So the problem could have batteries in the edges. It could have current sources into the nodes. It could fix U1 at some voltage like 10. We can also, our problem could fix, we must fix one of them. Otherwise, our matrix is singular. But once we've set up the matrix, and when we fix U4 equals 0, by the way, what happens to our matrix? Yeah. Let me take U4 equals 0. So this is a key step here. When I set U4 equals 0, I now know U4. It's not an unknown anymore. So I've removed U4 from the problem. And then it'll be also removed from A transpose A. So this is, you could say, like a reduced A or a grounded matrix A. It's now 5 by 3. And A transpose A, what shape will the A transpose A matrix be? It'll be 3 by 3, right? I now have 5 by 3, 3 by 5, multiplying 5 by 3 gives me 3 by 3. This column is gone, and that row is gone. Because the row came from A transpose, and the column came from A, and we've just thrown them away by grounding that node. Now tell me about give me the key fact about that A transpose A matrix. What do you see there? Now you see a reduced, a grounded A transpose A. What kind of a matrix have I got? Positive definite. Good. Positive definite. It's now not singular anymore. Its determinant is some positive number, and everything is positive. Its eigenvalues are all positive. Everything's good about that matrix. Okay. And I guess what I'm saying is, what I was starting to say here, if I wanted to know something, if I wanted to fix, this would be a natural problem, fix the top voltage at 1, say, fix U1 equal 1 and see how much current flows, right? That would be a natural question. How much, what's the system resistance between the top node and the bottom? If I'm given, or the system conductance, if I'm given a C1, a C2, a C3, a C4, and a C5, I could say I could fix that voltage at 1, I could fix this at 0. Maybe one of the homework problems asks you for something like this. And then you find all the currents. and the voltages. You solve the problem, and you know what the currents are. You know the total current that leaves node 1, enters node 4, when the voltages drop by 1 between, right? So current can flow down here, cross over here, down here, whatever. Somehow all these 5 numbers are going to show up are going to play a part in that system resistance. So that would be an interesting number to know. Out of those 5 numbers, somehow 5 C's, there's a system resistance between that node, and we can find it by setting this to be 1, this to be 0, having the reduced matrix. Oh, well, what will happen? How many unknowns will I have? Yeah, just do this mental experiment. Suppose I introduce U1 to be 1, for example. This is just one type of possible problem. If I take U1 to be 1, what happens to my matrix A? It loses its first column, too. U1 is not unknown anymore. U1 will not be unknown. And whatever, that value 1 is somehow going to move to the right-hand side, right? People have asked me after class, well, what happens if the boundary condition isn't 0? Suppose we have these fixed springs and we pull this spring down to make its displacement 12. Well, somehow that 12 is going to show up on the right side of the equation. It's a source term. It's an external term. Okay, so if we had U1 equals whatever, this U1 would disappear. I would only have a 2 by 2 problem. Because I would only have 2, I now have only 2 unknown U's, right? So that's where sources can come. And can I just complete the picture of the source stuff? We could, look, here's what I'm going to say. So external stuff, sources, can come into here. They can come into here. They can come into here. So, of course, everybody says, why shouldn't they come in here? And the answer is we could send them here. So we could fix some W's also. Of course, you understand, we can't do everything. I mean, there's a limit to how much we can put on the system. We want to have some unknowns left, some matrix still. But anyway, I like this picture now. It's more complete. That you now see the node variables and node equations, the edge variables E and W, the currents. These guys are the big ones. W and E and U are the what I think of as the crucial unknowns. E is sort of on the way. F is the source. But now we have the possibility of sources at all 4 positions. Okay, so that's, let's see. If I wrote out, I don't think maybe, yeah, if I looked at A transpose CA, would you like to tell me? Yeah. Have we got? No, we don't. I was going to say, what's a typical row of A transpose CA? Can I just say it in words? It'll be too quick to really catch. So without the C, this is what we had. So what do you think that 2 becomes if there's a transpose CA, if there's a C in the middle? Have you got the pattern yet? That 2 was there because of 2 edges. Edges 1 and 2 it happened to be. So instead of the 2, I'm going to see C1 plus C2. Right. When those were 1s, I got the 2. So this will be C1 plus C2. This will be a minus C1, and that'll be a minus C2 when we do it out. And you could do it out for yourself. Just tell me, what would show up there in A transpose CA. So I'm talking now about A transpose CA. So instead of 1 plus 1 plus 1, what do I have? What am I going to have? And you really want to multiply it out because it's so nice to see it happen. What do I have? I'm looking at node 2. I'm seeing 3 edges out of it. And instead of 1, 1, 1, I'll have C1 plus C3 plus C4. C1 plus C3 plus C4 will be sitting here. And minus C1 will be here, and minus C3 will be here, and minus C4 will be there. Yeah, yeah. The pattern's just nice. So if you can read this part of the section, I'll have more to say Friday about the A transpose W, the balance. That critical point we didn't do yet, but the main thing, you've got it.